Cable tray or conduit? Which route fits? Look, if you spent any time at all looking at industrial or commercial project designs, you are already intimately familiar with this classic engineering debate, right? It's honestly one of the most common and sometimes frustrating decisions project managers and EEs have to make. But what if I told you that the very premise of this debate, this whole idea that you have to choose just one or the other and argue with contractors about it, is actually holding your project back?
Welcome to this explainer. Today, we're going to completely shift our mindset on how we approach industrial routing. We're going to break down why these two very distinct systems actually solve fundamentally different routing problems. And, as you'll see, the most optimized, resilient, and cost-effective approach isn't about picking sides at all. It's really about understanding exactly how to blend them together.
Okay, let's just dive right in. Here is our structural roadmap for today. First, we'll hit the great wiring debate. Second, the 6 design factors. Third, where each system wins. Fourth, the ampacity reality check. Fifth, designing hybrid routes. And finally, built to global standards.
So, Section 1, the great wiring debate, moving beyond that old either-or mentality.
You know, for decades now, there's been this constant friction between using tray versus conduit. And let's be honest, it's often driven by just pure habit or outdated site preferences rather than actual engineering logic. But here's the thing. The answer is rarely all tray or all conduit, because they solve completely different problems. The ultimate solution is a hybrid system. It's about putting each system exactly where it performs best. By doing this, you aren't compromising at all. You're actually maximizing the strengths of your entire electrical infrastructure for your specific build.
Moving on to Section 2, the 6 design factors. This is our practical decision framework. And this brilliantly illustrates how we actually make those choices. When you're looking at any route, you need to evaluate 6 key factors: cable volume, environmental hazards, EMM shielding, future flexibility, heat dissipation, and physical protection. By weighing these specific factors side by side like a giant puzzle, this framework literally takes the emotion out of the process. It naturally points you toward the absolute optimal choice for that specific segment of the run, eliminating all the guesswork from your site plan.
Which brings us to Section 3, where each system wins, the head-to-head comparison.
So let's compare them directly. On one hand, cable tray absolutely thrives where flexibility and high cable volume are paramount. It offers far superior heat dissipation for high ampacity runs and makes moves, adds, and changes so much easier. But on the other hand, rigid conduit is just undeniable in hazardous locations or high traffic zones. When you absolutely need crush resistance and routing integrity against harsh environments, conduit is your go-to. Knowing when to deploy which, that's the hallmark of truly intelligent design.
Now for Section 4, the ampacity reality check. Let's dispel some open tray myths.
Before we go plotting our hybrid routes, we have to address a pretty dangerous misconception. A lot of designers kind of just assume that moving to an open tray system is this magic bullet that automatically improves ampacity. Well, actually, scratch that. It doesn't. An open tray doesn't give you a free pass on the laws of thermodynamics and current carrying capacity.
So, the crucial point here is understanding the derating check. You never want to just assume open air does the heavy lifting for you. If you skip this technical assessment, you are literally risking melting insulation, failed inspections, and, worst-case scenario, catastrophic failure. You have to ensure that your hybrid designs remain completely safe, structurally accurate, and absolutely code-compliant under real-world loads.
Okay, Section 5, designing hybrid routes. Let's translate this theory into practice.
Let's move to a sequential workflow and see how this builds out. Step 1, design the hybrid route. Simple enough. Step 2, establish those mechanical transition points. But Step 3, Step 3 is where most projects just bleed money. You must show these transition points on your drawings before procurement. Think about it. If you're figuring this out when materials are already sitting on site, you are guaranteeing costly delays and severely compromised engineering. So, plan the hybrid, map the transitions, and get it on those blueprints early.
And finally, Section 6, built to global standards, exploring the Xinma advantage.
Now, what's really interesting about this slide is looking at execution. To pull off a high-level hybrid design, you absolutely need high-level components. Just look at the sheer scale of the environments Xinma is manufacturing for. We aren't talking about your standard office spaces here. They're creating intelligent cable management solutions, busway systems, and seismic bracing for sectors where a routing failure is literally catastrophic. We're talking global data centers, massive rail transit networks, heavy industrial plants, the whole shebang.
And how do they actually guarantee that kind of reliability? By adhering strictly to the highest international benchmarks. Whether it's the European IEC, the American NEMA, or British and Chinese standards, Xinma's rigorous compliance ensures that your meticulously planned hybrid design is built on a rock-solid, legally compliant, and practically indestructible foundation.
Which brings us to the ultimate question today. As you look at the blueprints on your own desk, is your next project going to rely on that outdated either-or mindset, just forcing a square peg into a round hole because, well, that's how it's always been done? Or are you ready to run the derating checks, apply the framework, and design the ultimate hybrid route? The tools are right here in front of you. It's time to build smarter.